we were discussing Einstein's theory of specific heat of solids. Actually, this is second part of the lecture on Einstein's theory of specific heat of solids. And in the earlier lecture, we have seen that this Einstein's theory is a quantum theory of a specific heat of solid based on the quantum theory of Max Planck. And this theory is based on some of the important assumptions. And these assumptions we have discussed in detail in the previous lecture, but for your convenience, I have again mentioned these assumptions on which the Einstein's theory is based on. So you can see I am just just going to read these assumptions because you have seen these assumptions in the previous lecture. That according to this Einstein's theory, each atom of a solid acts as a simple harmonic oscillator vibrating with a common frequency nu. It means frequency of each and every atom is same, monochromatic vibration. And the vibration of any atom is not affected by the vibration of the neighboring atoms. And to find the average energy per atom or per oscillator per degree of freedom, Einstein has utilized the Max Planck's formula, which is epsilon bar equal to h nu divided by e to the power h nu by kt minus 1. And in fact, another important assumption of Einstein is the degree of freedom of a molecule of a solid is 3, just like the degree of freedom of molecule of a monatomic gas. So these are the important assumptions on which the Einstein theory of a specific heat is based on. In fact, on the basis of these assumptions, we have discussed the derivation of the famous Einstein's equation for a specific heat of solid. And these results, which I have mentioned here in equation A and equation B, actually you have seen the deduction of these results in the previous lecture. So I have mentioned it here because our today's aim is only to discuss that how this specific heat depends on temperature and how this Einstein theory agrees with the experimental observation. So for that we will need the final result of the previous lecture. So I have mentioned these expressions here, and you can see the equation A says that Cv is equal to 3r theta e over t whole square times e raised to the power theta e over t divided by e raised to the power theta e divided by t minus 1 whole square. In fact, you have seen in the previous lecture that this theta is what? This theta e is equal to h nu e by k, which is called Einstein's temperature. Here actually nu e is a characteristic frequency of a solid, and this particular frequency is known as Einstein's frequency. But before getting this result in the previous lecture, we have obtained the general expression for the Cv, and this expression reads as Cv equal to 3r times e raised to the power h nu by kt over e raised to the power h nu by kt minus 1 whole square times h nu by kt whole square. Actually, these results you have seen in the first lecture. Now, as it is clear from equation A or equation B that this Cv, which is a specific heat of solid at constant volume, that depends on temperature T. So our aim in this lecture is to discuss its temperature dependence, and for this we will particularly consider two regions of temperature. First of all, we will consider the high temperature region, and after that we will consider the very low temperature region. So let us see. First case we consider, this is when temperature is very high. Actually, to get the result in the case when temperature will be very high, let us simplify the expression e raised to the power h nu by kt minus 1 whole square in the denominator of equation B. So let us simplify it. So you can see I am just writing it in another page for convenience. You can see e raised to the power h nu by kt minus 1 whole square. You know, the expansion of e to the power x is known to you, as I hope. So let us use the expansion formula for this e to the power x to get the value of this expression. So you know e to the power x is what? This is simply 1 plus x square over factorial 2 plus x cube over factorial 3 and so on. Here at the place of x is h nu by kt. So what will be this? This is 1 plus x, but x is h nu by kt. 1 plus x plus 1 over factorial 2 times h nu by kt whole square plus 1 over factorial 3 h nu over kt whole cube and plus so on. And this term minus 1. So write here minus 1 2 and whole square. Now you can see this 1 and this 1 will cancel out, and as you are considering that temperature is very high, when you say temperature is very high, and you can see in each and every term T is or T square or T cube, these are present in fact in the denominator. So actually when T will be large, then the higher order terms h nu by kt will be very small. When t will be large, then t square, t cube, this will be very and very large. And so all these higher order terms will be negligibly small in comparison to this h nu by kt. So you can neglect all the higher order terms in this expression, and so our result will become e raised to the power h nu by kt minus 1 whole square. This will be simply equal to what? H nu by kt whole square. H nu by kt whole square. We have actually here we have neglected all the higher order terms, and this one have been cancelled out. So now let us use this value of e raised to the power h nu by kt minus 1 whole square in this equation B. So using this in equation B, we will use it. So you can see what will be the expression for CB. See this formula. This is 3R, so write here 3R, and in numerator there is e raised to the power h nu by kt. So write it into e raised to the power h nu by kt and over e raised to the power h nu by kt minus 1 whole square. But you have seen that this factor is equal to simply e raised to the power this is simply equal to h nu over kT whole square. So this is h nu over kT whole square and times what is here? This is h nu by kT whole square. You can see h nu over kT whole square. So this term and this term will cancel out and our result will be 3r times this much. You can see. Now again expand this exponential function. So what will be this? This is 1 plus x. X is h nu by kT. H nu by kT plus 1 over factorial 2 h nu over kT whole square and so on and so on. But as we are considering that this temperature T is just very large. When you say T is very large, mathematically you can say that this T is tending towards infinity. So when T will tend to infinity, then you can easily see that this h nu over kT will tend to what? This will tend to 0 because T is tending towards infinity. So all the terms inside this square bracket containing this factor h nu by kT can be assumed to be 0 when temperature will be very large. So this term is 0, this term is also 0. So inside this square bracket there will remain only 1. So you can see in this condition the expression for Cv will be simply equal to 3r. Can you recognize this result? I am asking you, have you studied this thing or not? Definitely you can recognize. You have seen in the first lecture on specific heat of solid, that is the classical theory of specific heat of solid, you have seen that this is classical result for the specific heat of solid. So you can see this Einstein's theory or Einstein's formula becomes simply the classical result, but when at high temperature. So you can say that at high temperature Einstein's formula for a specific heat and classical formula or Dulong-Petit's law for specific heat are completely identical. So you can say according to Einstein's equation, the atomic heat or the specific heat capacity of a solid approaches 3R at high temperature, and this is actually in good agreement with the experiment. So this implies, or you can say this is your classical result. This is classical result, and it agrees with the experimental observation. Because experiment says that at very high temperature the specific heat of solids become constant, and that constant value is simply equal to 3R. Actually this result have been also seen in the classical theory and in the Einstein's theory too. So you can say our classical theory of specific heat is not wrong, it is limited. It is in fact valid only when temperature will be very large. Actually in low temperature region the classical theory fails. So now let us see what will be this specific heat of solid when we will talk about the low temperature. So in second case, we are going to discuss the specific heat of solid when temperature is low. So when T is small or low, you can say. When you say small or very small, mathematically you can say that this T is tending towards 0. So what will be the result in this condition? You can see. You can see easily that if you consider in extreme condition that this T is tending towards 0, then h nu by kt will tend to infinity. You can easily say, because T is 0, and when you will divide a non-zero by 0, the result is simply undefined. So in this condition, you can see what will be the expression for Cv. We will again start from this general result which we have mentioned in this equation B, and as you can see in the denominator there is e raised to the power h nu by kt minus 1 whole square. But since in this case when t tends to 0, you have seen that h nu by kt is infinity, so e raised to the power h nu by kt will be very, very large in comparison to 1. And so in the denominator of this equation B, we can neglect this 1 in comparison to e to the power h nu by kt. And so neglecting this 1 in the denominator, in the case of low temperature, you can write the expression for Cv, and that will be 3r e to the power h nu by kt into h nu by kt whole square, h nu by kt whole square. So you can write it here. So in this condition, the expression for Cv, as I have explained, you can see this will be 3r e to the power h nu by kt, and in the denominator, as I have told you, we will neglect 1 in comparison to e to the power h nu by kt. So this is e to the power h nu by kt whole square. 1 has been neglected, and times h nu by kt whole square. You can see. Now, see here, this e to the power h nu by kt and this square will cancel out. So this Cv is equal to 3r, 1 over e to the power h nu divided by kt times h nu by kt whole square. And let us consider this equation. Let us say this is equation 1. But now we will simplify a little bit the RHS of this equation 1, that is the value of Cv which have been defined in this equation 1. We will simplify it to some extent, and for this we will simply expand this exponential function e raised to the power h nu by kt. So see it here. So Cv is equal to 3r times h nu over kt whole square, and see the equation. H nu over kt whole square and 1 over e to the power h nu by kt. So e to the power h nu by kt will be now expanded, and you can see this will be 1 plus h nu by kt plus 1 over factorial 2 h nu over kt whole square plus 1 over factorial 3 h nu over kt whole cube plus so on. Now see, if you will if you will divide this denominator by this factor which is in numerator, you can see, then what will be your result? You can easily see. It means we can write this expression as 1 over 1 plus h nu by kt plus 1 over factorial 2 h nu by kt whole square plus 1 over factorial 3 h nu by kt whole cube and plus so on, and whole divided by h nu by kt whole square. You can write it. This term, this numerator may be used to divide this. You can see. Now, in the RHS, in denominator, each and every term will be divided by this h nu by kt whole square. So what will be your result? This is 3r times 1 over. See here, when you will divide this 1 by this much, this will be simply 1 by h nu by kt whole square plus h nu by kt divided by h nu by kt whole square. So this will be 1 by h nu by kt plus, and when we will divide this h nu by kt whole square, then that will cancel out and we will have only 1 over factorial 2, and in the next term there will be 1 over factorial 3 h nu by kt and plus so on. You can see. This will be our result. I hope you are getting the things, you are understanding. Have you any problem? I hope there should be no problem. Now, you can see our condition is what? Condition is t is tending towards 0. And when t will tend to 0, h nu by kt will tend to infinity. So you can see, when we will use that condition, that is t tends to 0, h nu by kt tends to infinity. So instead of h nu by kt, write everywhere infinity. You can write it. So see it. In this limiting condition, that when t tends to 0, then what will be Cv? You can see this is 3r times 1 over, see here, 1 over h nu by kt whole square. So this will be 1 over infinity whole square plus second term is 1 over h nu by kt. So this is 1 over infinity. Then the third term is 1 by factorial 2 and next term is 1 plus 1 over factorial 3 h nu by kt, and that kt is infinity. So you can see this result is what? This is 3r over, now 1 over infinity, that will be 0, and plus 1 over factorial 2 and plus infinity. So this is simply 3r over infinity, and that will be 0. So you can see that this Cv is tending towards 0. And this is actually the experimental fact, that when t tends to 0, you have seen in the previous lecture that when Cv of solids are plotted in against of temperature, then you have seen that the experiment says the experimental curve is like this. In fact, at high temperature this is 3r, and when temperature is very low, that is, you can take here t equal to 0, so you can see that Cv becomes 0. So you can say that this result actually agrees with the experimental result. So this implies agreement with experimental observation. So now see this equation here, which I have actually mentioned in this case. I have actually considered it as an equation. In fact, now this equation 1 may be put in a particular form in terms of the Einstein's temperature and Einstein's frequency. So you can write this equation 1. Now equation 1 can be written as Cv equal to 3r times theta E divided by T whole square times E raised to the power minus theta E by T. And say this is equation 2. This is your equation 2, let us say. Actually here you can see that this theta is what? This is called Einstein's temperature, we have seen, and this is defined as h nu E over k. And actually this nu E is known as Einstein's frequency. So due to the presence of this exponential factor, you can say that when t will increase, then actually this exponential factor will also increase due to this minus sign. When t will increase, theta E by T will decrease, but as there is minus sign, so you can say that E raised to the power minus theta E by T will increase with increase in temperature T. But if T will decrease, this factor will decrease, and when T will tend to 0, then Cv becomes 0. So according to this equation, you can say that this Cv is proportional to E to the power minus theta E divided by T. Because in low temperature region, this exponential factor will dominate over this algebraic function theta E by T whole square. So this will be the deciding factor, and this decides that with decrease in temperature, Cv will decrease non-linearly. And this is your non-linear part of your graph, you can see it here. But actually experimental value does not agree with this exponential variation of Cv. In experiment, it is found that in experiment we found that this Cv is proportional to T cube when T is small, not e to the power minus theta e by t. So Cv is, this is actually called TQ law. So in a strict sense, you can say that this Einstein's formula also does not agree exactly with the experimental observation. Although in a qualitative way, this implies that with decrease in temperature, the Cv will decrease in low temperature region. This is just a qualitative value. But in quantitative manner, it does not agree 100% with experiment. So definitely there is some fault in Einstein's theory too. In fact, what is that fault? That fault is actually the Einstein's assumption that the frequency of vibration of an atom is independent of the vibration of the neighboring atoms. This was actually a mistake by Einstein. In fact, since solids are closely packed structure, so definitely the vibration of any atom will be affected from the vibration of other atoms. But Einstein has mistaken here, and this is why that this TQ law is not obtained from Einstein's formula. But in qualitative way, you can say that Einstein's formula predicts that at low temperature, with decrease in temperature, Cv will decrease, and when T will tend to 0 Kelvin, then Cv also tends to 0. In fact, in this Einstein's temperature theta e, you can see here the term is nu e, which is called Einstein's frequency, and this Einstein's frequency actually is same for more or less several solids. But in some of the solids like copper, aluminum, iron, it is found that this nu e is not same, and that's why the experimental curve for these elements like copper, aluminum, iron do not actually coincide. You can see it here in this graph. If we write here at temperature T and on this axis the value of Cv, then it is found like this. You can see it. This is for, in fact, carbon, you can say, or diamond. This is for aluminium, and this is for silver. Sorry, this is for silver. Silver symbol is Ag. This is for silver Ag. So actually, in case of some of the solids, these curves do not coincide with one another. So in this way, you can say that Einstein's theory predicts the correct values of the specific heat for various elements as observed in experiment. That is, you can say that Einstein's theory is in good agreement with the experiments. However, as I have told you and I have shown in this graph, that in case of some of the elements like copper, aluminum, iron, carbon, or you can say diamond, that it is observed that the specific heat at low temperature decreases more slowly than predicted from the Einstein's theory. Not exactly these solids obey the Einstein's formula. So, although there is some fault in Einstein's theory, and what is that? Why that fault actually arises? I have told you that the assumption that vibration of an atom is independent of the vibration of other atoms, this was just a mistake by Einstein, and so Einstein's theory has been rectified by device theory.